In this video, we'll further explore the application of game theory to sustainability issues. I'll introduce the idea of a Nash equilibrium, show you how to determine a Nash equilibrium, and connect it to decision making. A Nash equilibrium in a two-player game is a pair of strategies, each of which is a best response to the other. In general, we expect players to choose strategies which produce a Nash equilibrium. That is, knowing the Nash equilibria helps us to predict the outcome of a game. Nash equilibria can be interpreted in the following ways. It represents a no regrets choice. Even after observing the opponent's choice, a player has no regrets for the choice they made. A Nash equilibrium can represent a self-enforcing agreement. Even if an agreement is non-binding, no player has an incentive to deviate from the agreement. Finally, a Nash equilibrium makes a viable third-party recommendation, in the sense that all players have an incentive to take such a recommendation. Looking at these descriptions, we can see that Nash equilibria are likely to describe how decisions are actually made, and that it's useful to construct sustainability solutions that correspond to Nash equilibria. Let's return to the advertising example we worked through in the last video. There, we identified dominant strategies for each player, finding that both companies should advertise. Since these dominant strategies represent each player's best response to the other player, this gives us a Nash equilibrium. Thus, this analysis suggests that both companies will choose to advertise, even though they would be better off if they chose not to advertise. In other words, in this scenario, the Nash equilibrium is not Pareto optimal. We can extract some of the reasoning from the advertising example to general principles about how decisions are made. When there is a unique Nash equilibrium, we expect both players to choose the equilibrium. That is, we can predict what decision will be made. If both players have a dominant strategy, the dominant strategies give us a Nash equilibrium. Finally, the Nash equilibrium may not be Pareto optimal. In other words, game theory allows us to see how the market system may not lead to outcomes that are best for all. We've seen that if each player has a dominant strategy, the pair of dominant strategies gives a Nash equilibrium. To finish the video, I'll share an example where neither player has a dominant strategy and determine the Nash equilibria. Suppose two countries A and B share a lake along their common border. They each have the option to let their industries continue to pollute or not. If neither country pollutes, they gain the benefits of a clean lake. If just one country pollutes, it will gain economically, but the other country will lose some quality of life. If both countries pollute, the lake will pass a tipping point into a eutrophic state, and both countries lose severely. Recall that we discussed the possibility of such a tipping point earlier in this semester. Here's a possible payoff matrix for this scenario. Suppose B doesn't pollute, then the best strategy for A is to pollute. But if B does pollute, the best strategy for A is to not pollute. Now consider the situation from B's perspective. If A doesn't pollute, the best strategy for B is to pollute. If A does pollute, then the best strategy is for B to not pollute. Note that there are no dominant strategies. For each country, their best choice depends on what the other country does. We can also see that there are two Nash equilibria, both combinations of polluting and not polluting. Note that these equilibria are both Pareto optimal, and that any change for either country would result in a loss for at least one of the countries. But these equilibria are also precarious, as they both have a clear free rider. One country benefits from the other country's choice to not pollute, while continuing to pollute themselves. Given this, these may not be politically viable solutions.